Welcome to pre-lecture for Class 18. We are going to continue to discuss the qualitative behaviors of linear constant coefficient homogeneous systems. So let's go look at a couple of phase portraits on the next page. I'm going to review 4 of the systems that we saw last time we were in class. Remember that these are the matrices associated with the linear system of ODEs, x prime equals ax. And in a system like this, the origin is the only equilibrium point. Our goal is to understand what kind of equilibrium point we have, in particular, whether it is stable or unstable, but also how the solution trajectories are going to behave near that equilibrium point. In order to understand that, we of course have to plot some sample solution trajectories. And in order to do that, we find the eigenvalue-eigenvector pairs of the associated matrix of the ODE. In this case, our pairs are 5 with associated eigenvector 1, 1, and eigenvalue 1 with associated eigenvector -3, 1. Which one of these is the dominant eigenvector? It's the eigenvector associated with the larger eigenvalue. Why does that matter? It matters because it's the dominant eigenvector direction in which most solutions are eventually going to move. In this case, let's plot those two eigenvectors. The dominant eigenvector first is the 1, 1 eigenvector, and the other eigenvector is -3, 1. Notice that the solutions do eventually all move parallel to the dominant eigenvector, whether we are moving in the positive infinity or negative infinity direction. In this case, because all of our solution trajectories are moving away from the origin, that means that our one equilibrium point, 0, 0, is unstable. This is consistent with what we saw last time we met in class. Both eigenvalues are positive, meaning our solution is going to grow as time goes to infinity, and therefore the origin is going to be unstable. Let's go to the next example lower on this slide. This was system 2 from last time. Here, if we write down what the eigenvalue-eigenvector pairs are, it turns out we have complex eigenvalues and eigenvectors. So of course they always come in complex conjugate pairs. Remember that we can't plot complex eigenvectors, but we do know that because we have complex eigenvalues, our solutions are going to be some combination of e to the 3t and cosine and sine 2t, which means we're going to have a rotation. How do we determine the direction of rotation? We know that there are a couple of ways. We can use the OD directly to plot sample trajectories. For example, let's look at the point 1, 0, and we see that when we plug the point 1, 0 into our ODE, the movement at that point is going to be to the right and down. In other words, the movement is clockwise. Alternately, we can use the theorem we discussed, and we see that entry C is negative and entry B is positive, indicating that the rotation is going to be clockwise. Again, in this case, our single equilibrium point 0, 0 is going to be unstable because all solution trajectories are moving away from it. Notice also that the trajectory shapes tend to spiral. That's going to be important later. Let's go to the next page and look at a couple more examples. This was system 6. This again has complex eigenvalues and therefore complex eigenvectors. Notice here, however, that there is no real part, which means that our solutions, instead of moving out or in, away from or toward the origin, the solutions are simply going to circulate around the origin following the same closed path. This also means that our equilibrium point at 0, 0 is considered neutrally stable. Once again, we can figure out the direction of flow either by plotting sample trajectory points or by simply using our theorem and noting that C is negative and B is positive, which indicates that we will have clockwise flow. Finally, let's go to system 8. In this case, we're back to having real eigenvalue-eigenvector pairs. Notice that one eigenvalue is negative and one is positive. In the case of the negative eigenvalue, our solutions will be moving toward 0. In the case of the positive eigenvalue, the solution moves out toward infinity. So what does this mean? Let's first plot the eigenvector lines. On the 2, 1 line, we are moving toward 0, so we indicate that with arrows moving toward the origin. And on the -1, 1 line, we're actually moving away from the origin, so we indicate that with arrows moving out. Now, which of these eigenvectors is the dominant eigenvector? Again, it's going to be the eigenvector with the largest associated eigenvalue. So that means -1, 1 is the dominant eigenvector. The implication for solution trajectories is that eventually every solution trajectory is going to want to align with the -1, 1 eigenvector line. And we can see that here. Suppose we start up here in the upper right quadrant and follow a trajectory. We first follow the trajectory moving toward the origin, but eventually we veer off and align with the -1, 1 trajectory. And we see the same thing happening from every start point. So even though we have one negative eigenvalue, overall, the 0, 0 equilibrium point is still considered unstable because there's only one exact line along which solutions will be driven to 0. Every place else, you're going to eventually move out toward infinity. There's a special name for a point like this. It's actually called a saddle point. In fact, each one of these cases that we looked at has a particular name and falls into a certain category. Let's go to the next page and see what those categories are. Here we're going to fill in a chart to categorize the kind of equilibrium points we can possibly get, assuming that we have a diagonalizable matrix A. There are some other special cases that we will also talk about in class, but for now, we're going to assume that we have two linearly independent eigenvectors. This gives us a list of the kinds of cases we have seen so far. When our eigenvector pairs are complex, we have to look at the sign of the real part of the eigenvalue. When the real part is positive, what we get is an unstable spiral. The origin is considered unstable. Now, those spirals can actually move either clockwise or counterclockwise, but they will always be moving away from the origin. Of course, as we know, we can use our theorem or sample direction points to tell us whether we are spiraling clockwise or counterclockwise. In the case where the eigenvector eigenvalue pairs are complex, but the real part is 0, we then have a center, and the origin is neutrally stable. As before, our path trajectory may be moving clockwise or it may be moving counterclockwise. Again, we can use the theorem or the differential equation direction field to figure out the orientation of motion. Finally, if the eigenvalues are complex but the real part is negative, we again have a spiral, but it is considered a stable spiral, and the origin is stable. And once again, we could move clockwise or counterclockwise, depending on what we learned from our theorem or from our differential equation direction field. Let's look at the three cases of real eigenvalue pairs. Suppose our eigenvalues are real, but one of them is positive and one of them is negative. That's considered a saddle point, and the origin is unstable. The eigenvector with the positive eigenvalue will have solution trajectories moving away from the origin, and the eigenvector with the negative eigenvalue will have solution trajectories moving toward the origin. And trajectories accordingly will eventually move in the direction of the dominant eigenvector. Let's look at the case where lambda is real and both lambdas are positive. We already know that this is going to make our origin unstable, and that's called an unstable node. Now, in the case of an unstable node, it is again the dominant eigenvector that is going to determine what solution paths are eventually going to align with it. So if I drew my trajectory something like this, we would know that this must be the dominant eigenvector. We may also encounter some special cases where the eigenvalues are real and positive, but also equal. And in some cases, when you have a diagonal matrix, you might find something interesting, which is a star node, and then you have essentially an infinite number of associated eigenvectors. In the case where both real eigenvalues are negative, we still have a node, but this time it is stable. The picture is very similar, except now trajectories are all moving in toward the origin. And similarly, in this case, it is possible to have a star node as well, if you have equal eigenvalues and a diagonal matrix A. Now, in class, we are going to look at how to categorize these, not just using eigenvalues, but looking at the trace and determinant of a matrix to make similar categorizations. But for now, let's move to page 7 of the notes to talk about what a fundamental matrix is. Here we introduce the concept of a fundamental matrix. Just as a reminder, remember that when we had a single ordinary differential equation that was second order, it was easy to solve, assuming that the solution form looked like e to the lambda t, as long as the coefficients were constant. However, once we allowed the coefficients to be non-constant, we found there was no general solution technique. Similarly, when we move to a system, as long as our matrix A is constant, we do have a nice general solution form. However, once we allow matrix A to take on time-dependent values, we again have no general solution technique. It turns out, however, that in either case, whether we have constant or non-constant matrices, there is some very useful theory with respect to what we call the fundamental matrix, which we'll define in a moment, that helps us move from a homogeneous solution to a driven solution. Of course, always talking about linear systems. Now, in case you want to know a little bit more about why the methods we have no longer work when A is not constant, there's a little bit of information written here, which I will let you read on your own in the notes. Let's go to the next page. Here we define what a fundamental matrix is. The fundamental matrix of a linear, homogeneous system of first-order differential equations is a matrix that we will call psi, whose columns are linearly independent solutions of our differential equations. So this gives us a really nice way to collect in one place the entire set of linearly independent solutions that we need to generate any possible solution to our ODE. Remember that the fundamental matrix is very connected to the idea of a fundamental set of solutions that we talked about with second-order differential equations. Now, to show that a given matrix is a fundamental matrix, we have to show two things. We have to show that that matrix actually solves the ODE system, and we have to show that the matrix is non-singular. We're showing that because we need to confirm that the columns are indeed linearly independent. So what is the consequence of this? It turns out then that any solution to the differential equation can be written as the fundamental matrix times a vector of constants. Now let's look at this special case of a matrix A that is constant and diagonalizable. In that case, we already know one possible matrix psi. It is in fact the matrix whose columns are made up of each eigenvector with e to its associated eigenvalue t. That makes a fundamental matrix for the ODE system x prime equals ax. Remember, our existence and uniqueness theorems from class 17 showed us that we can expect to have n linearly independent solutions, and each column of this matrix is in fact one of the n linearly independent solutions to the system. Now, of course, we know why the matrix columns are linearly independent. They are linearly independent because for the diagonalizable matrix, eigenvectors are linearly independent. So each column is a solution and each column is linearly independent. Together, we see why this is a fundamental matrix. It turns out the fundamental matrix is not unique because we can change basis and find a different set of linearly independent solutions as long as there are n of them. This second example shows another fundamental matrix with which we already have some familiarity. Our claim is that the matrix exponential e to the at is also a fundamental matrix for this ODE system. Pause the video and convince yourself that e to the at also serves as a fundamental matrix for the system x prime equals ax. Remember, first, you have to show that matrix psi satisfies the ODE, and two, you have to show that matrix psi is invertible, showing that it has n linearly independent columns. All right, let's show that psi is in fact another fundamental matrix of this system. First, let's show that psi satisfies the ODE. Let's go back to the Taylor series definition of e to the at to show this easily. The derivative of psi is, of course, then the derivative of e to the at, which is the derivative of the Taylor series form of e to the at. This should feel like a familiar exercise because we did this when we showed that we could take the derivative of e to the at and it ended up being a times e to the at. So we've confirmed that psi prime equals a times psi. Now, what about showing that psi is invertible? Well, briefly, we actually can show that e to the at is non-singular because e to the at times e to the minus at can be written e to the at minus t, which is e to the a times 0, which we have shown previously to be the identity. To be formally correct, we would have to show that e to the at times e to the minus at actually equals the identity using a power series. But in the end, that shows us that e to the at is invertible and that its inverse is e to the minus at. And therefore, putting parts A and B together, we have shown that matrix psi, when it is e to the at, indeed is another fundamental matrix for the ODE system. Okay, we're going to stop there. And in class, we're going to get a little practice looking at solving a 3x3 system using a traditional approach that we've already learned, and then finding the fundamental matrix. See you in class.